Have you ever noticed the beautiful swirling patterns milk makes the moment you pour it into your cup of coffee? It's mesmerizing. The way the white milk twists, curls, and branches out like tiny galaxies being born before slowly fading into that perfect creamy blend. What you're watching is a physical process called diffusion, the natural spreading of particles from one region to another. But here's the part most people never realize. That swirl you witness is actually time travel in miniature. When milk first hits the coffee, every thin white filament you see is like a record of the past. Each pattern reveals where the milk used to be. And as the swirl fades, it's as if the memory of its journey through the cup is slowly being erased with time. You are literally watching history dissolve. Now here's the twist. Can this miniature time travel phenomenon, this fading memory of milk, be used to train artificial intelligence models that can predict something like house prices? It sounds absurd at first, but the answer is yes. And it lies in a powerful mathematical object in physics called the Green's function. But how on earth does the diffusion of milk droplets relate to predicting the price of a house? What does swirling coffee have to do with real estate and machine learning? The short answer: hidden correlations. Just as milk particles at different spots in the coffee cup are correlated when they begin to mix, house prices across different neighborhoods and with different features, like square footage, number of rooms, or age, are deeply correlated too. And, surprisingly, both sets of correlations obey the same mathematical laws. So if this sparks your curiosity, stay tuned. You can access all transcripts, notes, and projects in the description below. Before we talk machine learning, let's begin with the physics. Imagine dropping a single droplet of ink into a still glass of water. At first, the ink stays relatively compact, but soon it begins to spread, curling outward, diffusing into the water until the entire glass turns a uniform shade. That process, the spreading of particles from high concentration to low, is called diffusion. And in physics, we have an exact mathematical equation that describes this spreading over time, the diffusion equation. Now let's use this equation, but for our milk example. The milk drop consists of many independent molecules, each wandering around randomly, bouncing off coffee molecules, slowly spreading. The equation that tells us how the milk density evolves over space and time is. Here, phi is the density of milk at some location r in the coffee and at time t. D is called the diffusion coefficient, a number that tells us how quickly the milk spreads. And the term involving the delta functions represents the initial droplet, the injection of milk at position r' at time t'. So far, simple enough. Milk spreads out in time. But now we want to answer a deeper question. If I drop a bit of milk at location r' at time t', what is the probability that I'll find it at some other position r at a later time t? For this, physicists use something extremely powerful, the Green's function. Think of the Green's function g as a map, a propagator, that tells you how the effect of that one tiny droplet travels through space and time. Mathematically, g of r and t, r' and t' is the solution to the diffusion equation for a single initial point source. It obeys this equation. And the beautiful explicit solution in three-dimensional space is this equation. At first glance, this may look like pure mathematics, but this function has a profound interpretation, one that will unlock the bridge to AI. The Green's function doesn't just tell us how the milk spreads, it also tells us how the density at one place in time is correlated with the density at another. In fact, the mathematical object that measures similarity, called the correlation function, is proportional to the Green's function. This means, the further apart two milk molecules move, the weaker their similarity becomes. The Green's function tells us how this similarity fades with time and distance. And here's the next key idea. Green's functions have predictive power. If I know the milk density at earlier times, I can predict the future density at any new location using this equation. This says, the future density at the position r and time t is determined by summing over all previous densities, weighted by the probability of diffusion given by g. So now we switch gears, from coffee cups and milk molecules to machine learning. In physics, the Green's function tells us how similar 2 points are through space and time. In machine learning, we use a kernel for the exact same reason. A kernel is simply a function that measures the similarity between 2 data points. Let's translate the variables. In physics, the input to the Green's function is location and time. In machine learning, our inputs are simply the features of a dataset, things like number of rooms, neighborhood, and square footage for house prices. We usually denote this feature vector as capital X. The output of the physics model, the milk density phi, becomes the target variable in a machine learning problem. For housing, this is the price, which we'll also denote by phi for consistency. And the Green's function becomes the kernel, written k as a function of position vectors x and x prime. This kernel measures how similar 2 houses are, just like the Green's function measured similarity of milk densities. Now here's the key translation. Similar to physics, in machine learning, the predicted value of our target variable for a new input, x prime, is computed by adding up contributions from all training data points, weighted by how similar they are. And when we approximate this using finite training data, we get. But instead of giving each training point equal weight, we introduce learnable weights, alpha sub j. Machine learning then adjusts these alpha sub j's through optimization, just like we tune model parameters in training. So what Green's function did for physics, predict the future, kernels now do for AI, predict the unknown. But there is one major difference between physics and machine learning. In physics, the Green's function is not guessed. We derive it from the laws of nature, from differential equations that govern the system. In machine learning, we have no such equation. We simply guess a kernel based on experience and see if it works well. Here is a table of commonly used kernels. Let's now switch the gear and talk about the magical part. The kernel trick. Some datasets look chaotic or impossible to separate in their current form. But what if we secretly move them into a higher dimensional space where patterns become clear? Remarkably, a kernel lets us perform computations as if we move to that higher dimensional space, without actually doing the transformation. For example, suppose we have a dataset in 2D forming 2 concentric circles, an inner circle labeled -1 and an outer ring labeled +1. If we want to use support vector machine for this purpose, we need to find a straight line to split the 2 classes. However, no straight line in 2D can separate them. But if we map each 2D point to 3D using the equation, suddenly the 2 classes are separable by a plane. But the beauty of the kernel trick is, we don't need to know this mapping. We never compute it. Instead, we just replace the dot product with a kernel in our learning algorithm. For a support vector machine, the linear loss function is replacing the dot product with a kernel. Now the SVM behaves as if we move the data into some high-dimensional space where separation is easy. But we did not pay the computational price. Now, let's zoom out. Kernels have one major limitation in machine learning today. We don't know the correct kernel for each problem. We need to first guess, then test and tune. In physics, we would never do that. We would solve the governing equation and derive the Green's function from first principles. So here is the million-dollar question. If the Green's function is the best possible similarity function for a physical system, can we find a differential equation for a machine learning system whose Green's function would be the best possible kernel? In other words, can physics show us the ideal kernel for each machine learning problem? No one knows the answer yet. But my best guess is this. If we find a physics system that is mathematically equivalent or dual to the machine learning model we're studying, then the Green's function of that physics system may become the optimal kernel for the machine learning model. And just like the swirling milk in your morning coffee reveals a hidden, fading memory of where it once was, perhaps the mathematics of physics can help AI remember, learn, and predict with the same natural elegance.